Okay. Okay, first let's try to understand what do we mean by percentage yield and percentage purity. Is the thing straight for the camera? Okay, it should be this way. Yeah, okay. Now the word yield, what does the word yield mean? Maybe you guys have already seen the answer. What does the word yield mean? Yes, I want raised hands. I want to see raised hands. I used to see a lot of, okay, Ajwa. Yes.
It is the amount of product that we obtain from a reaction.
Okay, good. But what does the word yield mean in English language? You know, it's a simple English language word. Do you know what yield means in simple daily language? You must have come across this word even in geography, you know, in agriculture, the yield of crops. Remember? Do you remember your geography of grade 6, 7? So yield of crops. Yes, Momina. Yes.
What is produced?
Yes, simple, produce. Okay, whatever is produced. And yes, Ajwa, your answer was also correct. Okay. Okay. So yield means produce basically. Okay. Now, why do we calculate percentage yield? What is its significance? This is important because you know, like yesterday we were talking about, you know, the product being formed from the reactants and everything. So that was the ideal situation. Like that's when we don't consider the loss of any reactants to the surroundings, but that's not 100%, right? Practically speaking, that's not 100% because some of the reactant is lost to the surroundings, you know. Even while you're cooking, your ingredients are not 100, the ingredients that you added, not all of them end up in the product. Some of them might be washed away while you were transferring you know, the vegetables from one container to another, or while you were transferring oil from one container to another. Some of the oil spills, some of the water gets spilled, and you know, some of it gets burned. Okay. And so yeah, the ingredients in the final product are not 100% what you started with, what you started off with, right? So percentage yield is the calculation of that thing. Like a percentage yield is the calculation that what is the difference between the ideal product value and the actual product value. I mean to say that percentage yield means that what is the difference between the ideal value of the product mass of the product, and what is the difference between the practical value, the actual, okay, the actual value, the difference between the two. Okay, the difference between the two. The difference between the two is what we are dealing with, okay, in percentage yield. How do we calculate percentage of anything? Percent, what does the word percent mean? Percent means out of 100, right? You all must be knowing that already. Percentage means out of 100. Okay, so that's pretty simple. If you know the math, let me, okay, let me use a simple piece of paper. Here, can you hold this for me? Okay, so percentage means out of 100, right? So if out of the ideal calculated value, sorry, if out of the ideal calculated value, you got whatever you got, you know, actual yield. I'm just giving it the name actual yield. So my names that the terms that I'm using is calculated value, actual value, or actual yield, or actual value, whatever. Okay. Then out of 100, if you had 100 of anything, how much value would you, what would you have got? Okay, so again, the ratio method, we cross multiply the actual value, the actual mass of the product will be multiplied by 100 and then divided by the calculated value. So this is the formula, this is the formula for percentage yield. What is the formula for percentage yield? That actual yield divided by the calculated or the ideal yield multiplied by 100. Okay, I'll talk about this in detail. Okay, but this is the ratio method. So I'm going to repeat this. This is the ratio method, right? So if in the ideal, if out of this ideal calculated value, I got this much, okay, then if the ideal value was 100, how much mass of the product would have I obtained? Okay, did you understand this? And so I cross multiplied actual value by 100 and then I divided by the calculated value. So I got this formula, percentage yield is actual yield multiplied by 100 divided by the calculated yield. Now let me talk in detail about this. Okay, first of all, what are the sources of the loss of product? Your book has given a few examples and you can keep cooking in your mind, you know, how the ingredients get lost in the process of cooking. Same way in the chemistry lab, in a chemical lab, the reactants also are lost to the surrounding. Another reason why the actual value is not the ideal value is not the actual value is that the reaction may not be complete, may not be totally complete. What does this mean? Maybe the reaction is reversible. Maybe the reaction is reversible, or maybe after some reaction, the reactants stopped reacting with each other due to some reason. For example, let me give you an example. Do you remember aluminum reacting with oxygen, and then aluminum reacting with oxygen forming an aluminum oxide layer on the top, which does not allow more aluminum, which is deeper, to react with the oxygen? So that's an example. So the reaction is not totally complete. Okay, as soon as you have aluminum oxide being formed, the rest of the that forms an impermeable layer that does not allow the deeper aluminum to react with oxygen any further. So that's an example of a reaction that is not totally complete. Also, then we have reversible reactions, meaning that the products go back to make the reactants. And so in that case, the product will be less than what you have calculated. Can the product be more than the ideal value? Can the actual value be more than the ideal value? Yes or no, Sundus? Can the actual value be more than the ideal value? No. No. The actual value cannot be more than the ideal value. It can always be less because no matter is being added. Okay, no matter is being added, but matter can be lost to the surroundings. Or there can be some error in weighing the reactants and products. You know, you might have come across some error. You might have committed errors, and we humans are prone to errors. Some loss during the reaction to the surroundings, or during transfer or handling of the apparatus. For example, separating the product. For example, while filtration, you missed some residue on the filter paper, or while washing, or while transferring from one beaker to another, some drops of the reactant were left in the old beaker, right? And so on and so forth. So so this I have already explained you. Okay, so if the calculated yield is giving us this much yield, then if we had 100, how much would we have got? Okay, then this is a worked example. Okay, I can see Mehdia's and Momina's hands raised, so I will let them ask question. Why did you guys lower your hands? What happened? You don't want to ask questions? Where did you vanish? Media? Okay. Iman? Yes? Yes, Iman? Iman? I have unmuted you. I cannot hear you. Hello? Okay. Okay, Mehdi, and the other one was Momina, right? Momina, did you want to ask a question?
No, miss, mistakenly I left my hand raised.
Oh, okay. Yeah, please. Okay. Okay. So you guys are clear about this? Okay, very good job. Okay, cross. Okay. So let's do an worked example, okay, of how to calculate percentage purity. This I got from your book. This is in your book. Heating 12.4 grams of copper 2 carbonate in a crucible produced only 7 grams of copper 2 oxide. And what was the percentage yield of copper 2 oxide? Now, I hope you guys know crucible, what that is. Okay. So I hope you guys know how to write the formulae and you know how to write the balanced chemical equations. If not, then you can watch, you know, my grade 6 and 7, grade 6 and 8 classes. Okay. So this is the balanced equation. Okay. Now from this equation, and it is balanced. Double check. Copper one copper here, one copper here, one carbon on the left side, one carbon on the right side, 3 oxygen atoms on the left side, 3 oxygen atoms on the right side. Okay. Now coefficients are 1, 1, 1. That means the ideal molar ratio is 1, 1, 1 according to this balanced equation. Okay, now let's see what are the actual moles. This was the ideal. Now what is the actual? So using the masses given in the question and using the formula for the number of moles, we divided the mass by the molar mass, and the molar mass of copper carbonate is 124. So 12.4 grams divided by Shamim. Thank you. Okay, so mass divided by the molar mass, 12.4 grams divided by 124.1 moles. And copper oxide, according to the question, the moles are 0.0875. Now, according to this ratio, this should also have been 0.1, right? But it's not 0.1. I mean, if you round it off, it is 0.1, but actually it's not, okay? It's 0.0875. So this is the actual value. This is the actual number of moles. This is the actual number of moles. Okay, so when the mass is 7 grams, okay. But now what should have been its ideal value? Because you see, we have to apply this formula, right? So we know the actual yield, which is 7 grams, but what is the calculated yield? I mean, according to the balanced chemical equation. So for that, okay, okay. Okay, so for that, what did I do? It should have produced 0.1 moles. Okay, it should have produced 0.1 moles. And so if the moles were 0.1, then by multiplying it by the molecular mass, which is 80, I know that the ideal mass should have been 8 grams. You know, why isn't this camera straight? Yeah, okay. So this is the ideal mass. Okay, so again, now plugging in the values in the formula, the percentage yield is actual mass divided by the calculated mass multiplied by 100. So the actual mass was 7 grams. Okay, this was given in the question. 8 grams is according to the molar ratio, our calculation. Okay, the moles should have been 0.1 And when I multiplied that by the molar mass, I got 80 and I got 8 grams. So this is my ideal value. So 7 grams divided by 8 grams multiplied by 100, and I get 87.5%. Okay, so 87.5% is the percentage yield for copper oxide from copper carbonate. Okay, did you understand this calculation? Is there anybody who wants to ask a question? Is there anybody who is unclear? Okay, Ahmad 31. Yes? Yes, Ahmad?
Yes, teacher. Teacher, from where do we know the ideal mass?
Ideal mass is, okay, I'll explain you how I got the ideal mass. Ideal mass is what I'm using the molar ratio from the balanced chemical equation. Okay. So 1 mole is to 1. So the ratio is 1:1. So the reactant, the mass of reactant, the number of moles of the reactants are 0.1, right? So using this 1:1 ratio, this should also have been 0.1, right? Okay. If it were 0.1, then the mass would have been 0.1. Again, mass of the substance, what's the formula for the mass? Number of moles multiplied by the molar mass. You already know that, Ahmad, right? You already know this, right? Mass is the product of number of moles multiplied by the molecular mass. So this is my ideal number of moles. I multiplied that by the molar mass to get the ideal mass. Okay, did you understand, Ahmad?
Yes.
Yes, okay. Okay, so should we move on? No more questions? Okay. Okay, then percentage purity. Now, what is percentage purity? Let's talk about the term first. Percentage purity is like how pure a substance is. Because you see, the product that we get usually at the end of a reaction is not all the time 100% pure. It might be contaminated by the reactants. It might be contaminated, by the water with which maybe you washed your beakers. Okay, or even in when we extract minerals or when we extract metals from their ores have a lot of contamination, a lot of other unwanted substances mixed with them. And so these are all the examples in which it is important to calculate the percentage purity. Okay, and this is extremely important in medicine because we want the medicines to be highly pure. So how do we pure them? By repeated distillation. Repeated distillation meaning trying to evaporate off the impurities so that we have the pure things left behind. And then, crystallization and then crystallizing them. Yeah, okay. So now another example of purification of, another example where percentage purity is very important is, remember in the chapter of electrolysis, we talked about purification of copper. And why was it important? Was because we want 99.999% pure copper for electrical wires. We cannot be 100%, but we can approach 100 as close as possible. So 99.9999. Why is that purity important in electrical wires? Does anybody remember? I discussed it in electrolysis. That was before Ramadan. I will be really impressed if anybody remembers. Yes, Sundas, okay?
Because the impurity affects the conductivity of the substance.
How? Yes, that's correct, but how?
So having more impurities might decrease the conductivity.
Why? How? That's the question. Because remember, in metals, the conductivity is due to the flow of electrons, remember? Do you remember the structure of metals?
Yeah.
Sea of electrons, cations embedded in the sea of electrons. So electrons are flowing and that's how metals conduct, right? Impurities are like big boulders sitting on the way of electrons. They are like big boulders sitting in the way in the pipe or in the tunnel through which the electrons are flowing. Think of wire as the tunnel, and those impurities at big boulders or hurdles that the electrons have to. So those are impediments for the electrons. Do you understand? So that is why it's extremely important for these electrical wires to be as pure as possible. Why? Because you see, the more impurities you have, the more Akbar, be careful, your video is being on. Okay, so because you see, if we have impurities and if we have, you know, conduction being affected, a lot of electricity will get wasted, because you see excuse me, because you see, you know, when the electricity is being produced from power plants and, you know, is being transported or transmitted to different industries and houses, you know, and if the wires are not 100% pure, and if a lot of electricity is being lost, you know, in the way, that will be a huge economical burden on the country, and we will be losing a lot of power before it is even being used, right? So that is why it's very important. Okay, so once we have talked about the importance, now let's find out how do we calculate it. So total mass, if for example in the total mass meaning impurities plus the pure substance. Impure, you can call them impurities or you can call them contamination, whatever. Contamination also means impurity, unwanted substances. So total mass is the total mass, you know, combined mass of pure substance as well as the contaminated substances. If out of that total mass you get this much, you know, you can give it any value, any variable that you like. So out of this total mass, and you know, I can call it Tm, total mass, T for total, M for mass. So if out of this total mass you have X mass of pure copper, then if the total was 100, how much pure substance would you have gotten? Did you understand this? So this is again ratio method. I will cross multiply the values which are sitting across each other. So the mass of pure copper, if for example, I'm taking copper, okay, for explaining purposes. So mass of pure substance, it can be any substance, multiplied by 100 divided by the total mass of the impure substance. So what is left behind, you make that the denominator. Okay, so mass of pure copper multiplied by 100 divided by the total mass of impure substance. So that is our formula for calculating the percentage purity. Mass of pure substance divided by the mass of impure substance multiplied by 100. Okay, okay. And now I will take questions. Okay, okay. Ibrahim. Yes, Ibrahim? Yes, Ibrahim?
Miss, I want to tell that purity, but now someone told it, so I forgot it. Raising my hand.
Oh, okay. That's okay. So, okay. Okay, Zainab. Oh, sorry. Zainab.
Miss, when you wrote mass of pure copper divided by the total mass of the impure substance, that would mean just of the impure substance or the entire, like the total mass?
Yes, the entire total mass. Yes, the entire total mass. Total mass of the impure. What I mean by impure substance is not just the impurities, but you know, impure plus pure. I mean, total whatever you have, the total of everything that you have, okay, from which you are taking out the pure substance. Okay, we will do questions and you will understand. Okay, okay. Is there any other question? Okay, let's move on. You know, first I thought that disabling this chat permanently would deprive you guys of, you know, your chance of asking questions, because this experience is telling me that no, this is the best way, you know, because the actual questions are asked when you have enough confidence to come up and ask. Only those questions deserve to be answered. If you don't have the courage to come up and ask, then I think those questions should better be left alone. Okay, now let's talk about the gases. Okay, let's talk about gases. And there is a very interesting uh, thing about gases, which is very different from solids and liquids. Okay, we cannot weigh a gas, right? Because I mean, we could weigh the liquids and solids. That was easy. Just put them in a container and put them on a weighing balance, have the reading, calculate their tare values, and you will get the mass of the solid or the liquid. But can we do that with a gas? No, we cannot do that with a gas, because gas molecules are farther away from each other. They are banging against the walls of the containers. So they don't, you know, like their weight is not acting directly downwards, and therefore it is not easy to weigh them. Okay, if you have listened to my class on pressure, physics pressure, there I have talked about the, you know, what's the difference between the pressure exerted by the gas and the pressure exerted by the solids and liquids. So because these gas molecules are, you know, randomly colliding with each other, they don't, their weight is not, you know, directly downwards, and that even if it is directly downwards, it is being compensated by their movement. Okay, so we cannot weigh a gas. So instead, it is easier to measure their volume. Okay, but remember, in our calculations, if you see, in our calculations, we are always concerned with the number of moles, right? We are always concerned, what is mole? This is just a measure of particles. So we are interested in counting the number of particles. Now, if we cannot weigh gases, and if we can only measure its volume, then how can we translate the volume into the number of particles? How will we know? Like how will we know how many particles are there in a particular volume, right? So Avogadro, I think he was an Italian scientist. He came up with this law, and of course, this was a result of his experiments, that equal volumes of gases contain the same number of particles. Okay. Another thing that I want to mention here is that, you know, in your books and every time and everywhere, you always hear these the names of non-Muslim scientists, right? Italian, French, American, this and that, British. But I want to emphasize and I want to mention that there are many, many, many Muslim scientists. Okay. Gibran bin Hayyan, and they were the pioneers of chemistry. They were the pioneers of chemistry. In fact, many of the names, the word chemistry itself is actually a derivative of an Arabic word kimiyai. So the foundations of chemistry were kept by Muslims, but because these books are unfortunately written only by non-Muslims, they don't emphasize, they don't mention, okay, because they are biased. Okay, so I want to mention this to all of you, to all my chemistry students, that that's not the case. The actual basis of chemistry was kept by Muslim scientists, okay, when Muslims were following their religion. Unfortunately, we don't follow our religion that well these days, and so therefore now these non-Muslims have overtaken us, and so everywhere you read their names. So anyway, so equal volumes of gases contain the same number of particles. Now, why is that, and how is that, and how, I mean, how is it possible that equal volumes of different gases contain the same number of particles? And do you know, any type of gas, I mean, it can be, they can be any type of gas, but as long as their volumes are the same at the same temperature and pressure, the number of particles will be the same. Now, let me explain this in greater detail. Why is this so? See, if for example, why this can, okay, yeah, okay. If for example, these are, for example, these are two balloons, or, you know, these are two, you know, whatever, containers. And I have taken 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6 ho gaye. Chalo. Okay, 6. So 6 particles. I have taken just random any number for your easy understanding. I have taken 6 particles, okay, in these 2 volumes. Now this is carbon dioxide, a gas, and this is hydrogen, another gas. Now can you see the molecular mass for carbon dioxide is 44 and the molecular mass for hydrogen is 2. Can you see the difference? This is so much heavier than this. This is so much heavier than this, right? But if these 2 volumes are the same, and also, if also the temperature and pressure are the same, if temperature and pressure are the same, the number of particles is going to be the same. Let me try to explain you why. Now, what is temperature doing? Temperature, what is temperature? Average kinetic energy, right? The more the temperature, the more they will jiggle and the more they will move away from each other, right? So temperature will try to increase the distance between them, right? The more the temperature, the more vigorously they will collide and they will move farther away from each other. And so they will occupy greater space. Now, when we talk about a volume of a gas, we talk about the space that they occupy, the way they are distributed. That also includes the distance between them, which is just empty space. This space is empty, there's nothing in it. But when we measure the volume, we are including this empty space. We are not just talking about these molecules. We're talking about the distance between them as well. So as the temperature increases, they move away from each other and therefore expanding and therefore increased volume. But what does the pressure do? Pressure does just the opposite. It tries to squeeze the particles together. It tries to squeeze the particles close together. And so increase in pressure decreases the volume. So both these factors are working against each other, right? Temperature is increasing the volume, pressure is decreasing the volume. Pressure decreases the volume and temperature increases the volume. So that is why it is important that when you are comparing 2 gases, and when you're counting their number of particles, temperature and pressure must be the same. Because if they are not the same, maybe, one gas has greater volume because the temperature is greater. That's why, it's more expanded. Or the other gas might be having smaller volume because the pressure is greater. So therefore, when you're comparing, make sure the temperature and pressure are same of both the gases. One thing. Second thing is that the molecules are so tiny. The molecules are so tiny. I cannot emphasize enough that their actual volume, the actual volume of the molecule itself is negligible. It's negligible compared to the whole space that the whole gas is occupying. Did you understand me? If I combine all these dots, and I calculate the volume, that volume will be nothing in front of the volume of this whole balloon. The volume of this whole balloon, okay? So we can easily and safely ignore the volume of that molecules. We can just assume, we can neglect it. So it doesn't matter how heavy carbon dioxide is from hydrogen. It doesn't matter. It doesn't matter how heavy carbon dioxide is from hydrogen, but if the temperature and pressure of both these gases are the same, and the total volume that it is occupying is the same,
Hello?
the number of particles will be the same. Iman, please mute yourself. Okay. Sidra beta, you are not doing your job, okay? Okay, so I hope you understood this. I hope you understood this. So this is why gases, no matter what type of gases they are, if they are at the same temperature and pressure and they have the same volume, they have the same number of particles. And another thing, 1 mole has 6.02 into 10 to the power 23 particles. That rule applies to even gases. That's true even for gases. This is true whether gas, solid, or liquid. Okay, so you can think that 1 mole, 1 mole contains 6.02 into 10 to the power 23 particles, and if you expand it, the number of particles will stay the same of 1 mole. Okay. Okay, another thing that Avogadro mentioned was that the volume of 1 mole is 24 dm cube. Okay, remember this. Okay, remember this. First of all, volume of 1 mole is always going to be 24 dm cube, not always, at a standard or room temperature. At room temperature and pressure. Okay, if you can, the periodic table that you get in your IGCSE exam, is this clear? There's this statement written at the bottom of periodic table: the volume of 1 mole of any gas is 24 dm cube at room temperature and pressure. If you can get this, if the printouts that you get from your the past papers websites, for example, this is from dynamicpapers.com. Okay, then you also get a periodic table at the end. This statement is written at the bottom of the periodic table. This means that volume of 1 mole of any gas, be it noble gas, be it carbon dioxide, be it oxygen, hydrogen, whatever. Okay, the volume of 1 mole of any gas is 24 dm cube at room temperature and pressure. And you know why it's important to keep the temperature and pressure constant. Okay, we discussed. Okay, another thing that you should remember is that 1 cm cube is equal to 1 milliliter. Okay, we usually use liters for fluids like liquids and gases, and cm cube is used for solids. Okay, cm cube is used for solids and liters is used for fluids. Okay, 1 dm cube is equal to 1 liter. Okay, 1 cm cube is equal to 1 milliliter, and 1 dm cube, dm stands for decimeter. Deci means 10. So 10 centimeters is equal to 1 decimeter. Okay, deci means 10. So 1 dm cube is equal to 1 liter. And because 1 cm cube is equal to 1 milliliter, 1000 cm cube is equal to 1000 milliliters. So this will come in handy when you will solve questions. Okay, so if you have understood this, is there any question? Okay, is there any question so far? Are you convinced that different gases at same temperature and pressure containing the same volume will have the same particles? Are you clear about that? Okay. Otherwise, you can raise your hand. Okay. Now, we are concerned with the number of moles, right? So, okay, we understand that. Okay, fine. But now, how should I translate that into the number of particles? Because for our calculations, we need the number of particles, right? Number of moles, in cases of solid and liquid, the formula was number of moles is equal to mass divided by the molecular mass, right? That was the formula for solids and liquids. Now, what about gases? Because in case of gas, we don't have mass. In case of gas, we don't have mass. Now, what to do? So instead of mass, we need volume. We have to use volume. So for gases, instead of mass, we use volume. For instance, how many moles in V dm cube of a gas? V is just a variable. Whatever volume that you have given in a question, or whatever volume you want to find out, I have given it a value, I have given it a variable V. So if we know that 24 dm cube is the volume of 1 mole, if we know that, this is Avogadro's law, 24 dm cube is the volume of 1 mole, then V dm cube will be how many moles? Again, ratio method. I will multiply the values sitting across each other. V dm cube multiplied by 1 mole divided by 24. So this is the formula for the number of moles of gas. that you divide the volume of the gas by the molar volume meaning volume of 1 mole, which is 24 dm cube, and you will get the number of moles of gas. And then if you did not understand this, I have made this analogy. This is simple analogy, simple. You used to do this in grade 1, 2, 3, 1, 2. Remember in grade 1, 2 math, when you were first introduced to the idea of division? The idea of division, let me explain you with this. For example, this is the total jar of sweets, okay? And then you have 4 packs in the big jar, and each pack has 4 sweets. Each pack has 4 sweets. Now there are 3 pieces of information that we have from this. The total number of sweets is 16. How did we know that? 4, 4, 4, 4. So 16, okay, 4 4s are 16. And there are 4 sweets in each pack, and there are a total of 4 packs. 1, 2, 3, 4. Okay, so if you remember in your division, the first time division was introduced to you, do you remember this? The total number is equal to the number of, you know, something in each group multiplied by the number of groups. Do you remember this? I'm sure that you must have in your grade 2, 3 math. So we're using the same concept. So total sweets can be calculated by multiplying the number of sweets in each pack with the number of packs. Now the same idea we're using here. You know, I have seen people ratifying the formula, you know, the number of moles is mass divided by the molecular mass, and then, you know, the number of moles is equal to, you know, whatever the formula is. I have never learned these formulae. I use this, and it's easy, very easy. Okay, total volume, same thing, total sweet, just like you get total sweets by multiplying the number of sweets in each pack. Number of sweets in each pack is the same as the volume of each mole. So think of this as 1 mole. This is your 1 mole. This is 1 mole, okay? So if I want to find out the total volume, what will I do? I will multiply the volume of 1 mole by the total number of moles. So I will get the total volume. And then we can play around with this formula. But it's okay if you, you know, for saving time, if you want to use that, you know, triangle thing that is shown in your book, you know, the thumb method, you, whatever you're trying to calculate, you hide it with your thumb, and whatever is left behind, you just follow that. Where is that triangle thing? Show me some of this in your book, that thing, that formula. So, okay, so did you understand this, that the total volume can be calculated by multiplying the molar volume, which is the volume of 1 mole, by the number of moles? So you will get the total volume. And so similarly, you can play around with this. You can play around with this formula. And so number of moles would be, what will be the formula now for the number of moles? Will be total volume. Is my camera showing this? Total volume divided by the molar volume. Okay, so this is the formula for gases. So if you want to find out the number of moles of gases, you have to use this formula. Total volume divided by the molar volume. And molar volume is always going to be 24 dm cube at room temperature and pressure. Okay, so one good news is that in calculating gases, you don't have to calculate the molecular mass. No need. You don't need to calculate the molecular mass because we are not using mass. We are using volumes, and which is the same no matter what gas it is. So you don't have to worry about calculating the molecular mass of gases. And that, by the way, is the first question at the end of chapter. Let's do it. Let's do it right now. Yeah, and this is the triangle I was talking about. So if you want to find out the number of moles, I will hide this with my, this is page 166 of your book, this triangle. So this is that thumb rule. So if I hide this number of moles, I am left behind with volume divided by the molar volume. Okay. And so question number one. Question number one at the end of this chapter, page 171. When working out the masses of solids, I hope you can read this in the camera. Okay. When working out the masses of solids that react with each other, we need to know their relative formula masses. When working out the quantities of gases in a reaction, this is not necessary. Explain why. Who will explain? Yes, Ahmad? Ahmad, it's okay. I know you want to ask a question. It's okay. Yes. Oh, sorry.
Teacher, I was saying the page is not clear.
Oh, page is not. You don't have the book?
No.
Okay, I did post its PDF in the group. Okay. Is this clear? Is it clear now? Is it clear now? Unmute karo. Karo na. Yes, tell me, Ahmad, is it clear now? No?
Yes, teacher, a bit.
Is it clear now?
Yeah, almost.
Almost. Okay. Tap the page. No. Tap the page. Why should I tap the page? Okay, I'm reading it. Okay, try to listen to me. When working out the masses of solids that react with each other, we need to know their relative formula masses. When working out, okay, please mute yourself. Okay, when working out the quantities of gases in a reaction, this is not necessary. Explain why. Who's going to explain? Who's going to explain why is it not important to calculate the molecular mass of gases?
I'm getting it.
Yeah, why is it? Yeah, okay, Momina, good job.
Because we know that at room temperature and pressure it is 24 dm3.
Yeah, no matter what the gas is, so no need to calculate, right? Okay, let me tell you guys something about Momina. Do you know that Momina is a grade 7 student? And all these months that I've been teaching, I thought she was a grade 8 student, you know, going to grade 9. And only recently I found out that she is just a grade 7 student, and I love her enthusiasm and the way she attends all my classes, and she participates very positively. And I just appreciate it. You know, I can only see, it's something like this, you know, we can only give you water. Drinking is your job. We cannot drink for you, okay? So people who can drink, please drink, okay? I'm saying, you know, I'm just using an analogy. This knowledge is like water. I can only give you. Taking is your job, okay? If you don't want to take, there's nothing I can do more than this. But I appreciate Momina, okay? May Allah help you, and may Allah give you success in this world and the hereafter. Ameen. Ameen. Okay, so once we have understood the formula for the number of moles of gases, now let's apply this. This is one example. For example, hydrogen reacting with chlorine, and now you also must be appreciating why it's important, why the state symbols are important, right? So we need to know if a substance exists as solid, liquid, or gas at room temperature. So these two are gases, and if these two are gases, then this would also be gas. Otherwise, it can dissolve in water to form aqueous acid. But if there is no water available, then it would be gas. Okay. So now, according to this equation, balanced equation, the molar ratio is 1:1:2. Okay. The volume of 1 mole is We know according to Avogadro's law, 24 dm cube, 24 dm cube, and because this is 2, so twice 24, which is 48 dm cube. So 24 dm cube, 24 dm cube, and 48 dm cube. Now remember, in solids and liquids calculation, I mentioned that the mass ratio is not the same as the molar ratio. Sorry, this is wrong. This is mistake. I meant to say molar. Sorry. Okay. So in solids and liquids, if you have watched those classes, or if you have attended those classes, if you remember, I mentioned that never use mass ratio, because molar ratio and mass ratio are not the same in cases of solids and liquids. Why? Because 1 mole of each substance does not have the same mass. 1 mole of each substance does not have the same mass. Some are heavier than others, some are lighter than others. But in case of volume, because 1 mole of all the gases will have the same volume, therefore the volume ratio is equal to molar ratio. So that makes things even easier. So if you know the volume ratio, you can just directly use the volume ratio. No need to convert it into moles. So that's another good news. Okay. So volume ratio is equal to molar ratio for gases only. But for that, you have to know if a substance is a gas at room temperature and pressure. Okay. Now, this is a worked example given in your book. Okay. And let's try to do it. I think I did it in another copy. Yeah, here. Okay, the question is, if 8 grams of sulfur are burned, what volume of sulfur dioxide is produced? So sulfur is a solid, it's a yellow powder, burning in oxygen. Oxygen is a burning gas, producing sulfur dioxide, which is a gas. According to this balanced chemical equation, the molar ratio is 1:1:1. Now, we can, the question has given us information regarding sulfur only in this question. So, okay, let's find out the number of moles of sulfur. Again, this is solid, so I will use the formula mass divided by the molar mass. Molar mass I got from the periodic table for sulfur is 32. 8 divided by 32 is 0.25. So because they did not give me any other information, so I will take this ideal molar ratio. I will use it. 0.25 should give me 0.25 moles of sulfur dioxide because the ratio is 1:1, right? So if 0.25 moles of sulfur, 0.25 moles of sulfur dioxide. So that means we have 0.25 moles of sulfur dioxide. So according to Avogadro's law, 1 mole has a volume of 24 dm cube. Then 0.25 moles will have, just multiply the number of moles by the molar volume, and so you will get the total volume of the gas produced. Therefore, 6 dm cube of sulfur dioxide is produced. So again, I'm using ratio method. I'm cross multiplying and dividing by 1. Simple. So 0.25 multiplied by 24 is 6 dm cube of sulfur dioxide. Is there any question regarding this? Please, you're most welcome to ask. It's okay. Is there any step that you want me to repeat or explain it to you again? You're most welcome to ask me. No? Everything is clear? Wow, you guys are real good. Okay, now, after we have done percentage purity, percentage yield, and then the number of moles of gases, let's do this question. This is question number 2 from the end of chapter questions. End of chapter questions, question number 2. And this is, for those of you who have the book, page 170. No, this is not question number 2. This is, sorry, question number 5. This is question number 5. Okay, page 172. For those who have the book, you can take out the book and, okay. A 5-gram sample of impure, so we have to calculate percentage of lead to nitrate, percentage purity. This is percentage purity. A 5-gram sample of impure lead to nitrate was heated. The volume of oxygen formed was 0.16 dm cube measured at room temperature and pressure. The impurities did not decompose. Calculate the percentage of lead to nitrate in the sample. So this is the same as percentage purity when we have to calculate percentage of a pure substance in the sample. This is the same way. I mean, this is the same as asking you to calculate percentage purity. They can either ask you calculate the percentage of the pure substance, or they can ask you calculate percentage purity, same thing. So again, first step is to write chemically balanced equation. This is already given in the question. Okay, this is already given in the question. So keeping this chemically balanced equation in mind, look at the molar ratio. 2:2:4:1. 2:2:4:1. Okay. So they have given us the mass of impure lead to nitrate. So again, I will use the formula number of moles mass divided by the molar mass of lead to nitrate. Lead to nitrate's molar mass is 331. Okay, so the number of moles is 0.015. Okay, and then the volume of oxygen formed is 0.16 dm cube. Okay, so now if I know the volume, I can find out the number of moles, right? How? 24 dm cube is 1 mole, and so 0.16 dm cube would be how many moles? 0.16 divided by 24. So I get these many moles. Okay. And so, okay, you don't have to calculate the number of moles. You can, directly, yeah, because you see volume is the same as the molar ratio. You don't have to calculate the number of moles as I told you, but I think I forgot that and I did this. But then I realized that, volume ratio is the same as molar ratio. So I went in and I put in the values directly, So the total substance, no, wait, what did I do here? So this is 0.16 dm cube, which got produced. And yeah, so according to the molar ratio, this should have been half of it. This should have been half of it, right? So half of 0.015 is 0.0075 moles. Half of this is 0.0075 moles. So if I multiply that by 24, I will get this 0.18 dm cube will be the ideal volume of the pure substance. No, sorry, this is the total substance. Okay, I did not get time, to prepare this. So if I find a mistake, I will mention in the next class. So, okay, so according to the values given in the question, the volume of oxygen produced was 0.16 dm cube, and the total volume ideally, the total volume is 0.18. Okay, so pure substance divided by the total substance multiplied by 100 gives us percentage purity. So 0.16 divided by 0.18 into 100 gave me 88.89%. Okay, which is the answer. Okay, is there any question? Please ask. Is there any question? Please ask. Okay, calculate the percentage of. Yes, Ajwa, Ariba, Fatma, Hamza, Hania, is there any question? Hania, is there any question? Hania, you did these questions even, before I explained, so I'm sure that you know them very well. No question? Okay then. Laiba, did you understand? Okay, okay then, inshallah. Then please follow my schedule for the next classes. Okay, I'm ending the meeting. Assalamu alaikum wa rahmatullahi wa barakatuh.